I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for the students, and just ask you to bless this class today, Lord. In your name I pray. Amen. So, this is a handout my brother prepared for a course he taught in Galois theory at Appalachian State University. And so I think he took the final part of his course to talk about differential Galois theory after he'd spent about 2/3 of the course on Galois theory. So, you know. So there's a little bit of a compression in here, relatively speaking, right? But that's a lower level course in some sense. And well, the other difference is I won't actually test you guys on this that seriously. The level of my testing is sort of you already seen it in the mission, all right? That's kind of like as far as the kind of question I'm going to ask goes. So if you just listen to the words coming out of my mouth and understand that what I'm doing at a somewhat fuzzy level, you should probably be able to answer my question about differential Galois theory. I'm more trying to just make you aware that there is such a thing and how it is very much analogous to Galois theory, all right? So in order to get to that point, which will be Friday, we first have to build some sort of basic differential field theory, all right? So this is sort of the analog of chapter 13 in some sense, what I'm talking about right now. So first of all, definition, if we have a ring, a commutative ring with unity, a map partial from R to R is a derivation if it's linear in Leibniz. In other words, if it's additive and it obeys the product rule, right? So a ring equipped with a particular, and this is called a derivative, a ring equipped with a particular derivative is called a differential ring. And so we can write like partial A is A prime if we want. So if R is a differential ring and also an integral domain, it's a differential integral domain. And if R is a differential ring and a field, it's called a differential field. So now Bill gives us some examples. Some of them familiar, some of them less familiar. So if R is a differential ring, first of all, you can prove that the derivative of 1 is 0. All right, that's generically true because it follows just from the Leibniz rule and the additivity, right? You can also see that the derivative is a group homomorphism in the sense that if we add, with respect to the additive group structure here, like the derivative of n times a is n times the derivative of a. So like we can break up across repeated addition is what he's saying, right? That's that notation. So it's a group homomorphism in that sense. And of course that gives us that the derivative of any, if we repeatedly add 1 to itself, that's also differentiating to 0, right? So everything in the prime subring, right, because we generate, the prime subring is what? It's either Z or ZP, right? Remember? And then we build the field of fractions over that to get the prime subfield. This is that discussion again. So anyway, anything in the prime subring from which we build the prime subfield for a given field has derivative 0. Also, now what's he doing now? He's basically getting a sort of chain rule, right? Well, in fact, he's building the power rule. So if we have a to the n, you know what? There's a typo here. That's supposed to be an to the what? An. Let me see if I can make this a little bit bigger. How's a zoom? I should try to be somewhat. Let me just take it.
I think I've got it.
You got it pretty optimal? Okay, cool. You said good job, Liam. You guys are so encouraging to Liam.
So encouraging.
I know.
Just like our
It's good.
chat picture.
Yeah, I saw the group chat picture. It's perfect.
Just pilfer my points and put red X's.
If I had the time in my life to type up proper course notes for this course, which is unfortunate, right? I found time to write some pretty decent lecture notes for 421. I haven't found that time for 422 yet. Partly because the subject matter is such, so much more deep. But if I did, surely that would be the great picture to put as my cover art,
Please do.
That would honestly be great.
So the derivative of a to the n is this, all right? In addition, if we have a unit, right, which is one with a multiplicative inverse, then you can calculate this, and then by the product rules that. So you get this formula for the derivative of the inverse, right? The derivative for the inverse is minus a to the minus 2 a prime. So that's essentially like the quotient rule written abstractly for 1 over a, right? The quotient rule for 1 over a looks something like the derivative of a divided by a squared with a minus, right? That would be our usual derivative for a quotient, yeah? And you can extend this by induction to all integers. So we have the, and again, I got to talk to Bill. I mean, he may have fixed this by now. I think I put this on my computer about 2-3 years ago now. But I should actually communicate to Bill, hey, your handout's missing a prime right here. All right. Now, okay, great. So then we can extend then. So what we're doing is we're building up the structure of calculus just using the fact that we have a derivation in the sense something that's additive and obeys the Leibniz rule, right? There's no limits here, right? This is just all formal algebra. A formal algebraic mockery of calculus, really. Without, I mean, in the limiting sense, there's no limits here, you know? A and B, B has a unit, right? Then, so this is like the derivative of A over B. So next up, he derives the quotient rule just using the derivation, right? So we have a quotient rule like that. So in particular, since we've already shown that the derivative of the integers in the prime subring of the ring in question have derivative 0. This shows that the derivative of any rational number built in the prime subfield is 0. So the derivative of any anything in the prime, any constant in the prime subfield is 0 in a differential ring. This is not especially surprising, right? The derivative of a constant is 0 in these differential rings. All right. Next up, you can do the same thing that we do in 421. If you have an integral domain, and it happens to also be a differential integral domain, you can build the field of fractions over it, and you can extend the derivative to the field of fractions. And so you can take a differential integral domain and convert it into a differential field by looking at the field of fractions. And when you do that, the way the derivative extends to fractions is exactly by the quotient rule. So this unambiguously defines how we extend the derivative to the field of fractions if you already have a derivative defined on the ring. Definition: a differential subring is a subring containing 1, which is closed under differentiation. So S, the subset of R, is a differential subring if 1 is an S, and A, B, and S implies that A minus B and AB is an S. Well, up till now, what's this? This is just plain old 421 standard fare subring test, right? But then what? Also, A implies that the derivative is also, so it's also closed under the derivative operator. So there's a new string attached to the derivative, right? So differential subring. Very satisfying. You can also define differential ideal. That's an ideal which is closed under differentiation. Ideal in the sense we defined last semester, right? Closed under the Uber multiplication. And if we have a differential ideal and we quotient by a differential ideal, it becomes a differential ring, provided we define the derivative on the cosets just by the derivative of the representative of the coset. Again, you can show it's well defined. And a differential homomorphism is going to be a ring homomorphism which also respects the derivative. So it's a map from R to S, which is a ring homomorphism. In other words, additive, respects the multiplication, tends to 1 to 1, preserves differentiation. How's that work? Well, the phi of the derivative is the derivative of phi. Hey. No. That should be what? Like that, right?
Is that, I mean, I think that's what
Oh, is it? Am I? Oh, I see. It's an unfortunate end to a parenthetical comment, is what you're saying. That's this one and that one. Oh, okay. So, as a matter of taste, I think he at least needs like a space here. You know, whatever. Or better yet, say it like this: phi of partial a is equal to partial phi of a. Right. But of course, the derivative on one side and the other are the derivation of the domain versus the derivation of the codomain. Yeah, they're different derivatives in principle. But anyway, a differential homomorphism preserves the derivative in this sense. Oh, guess what? The kernel of a differential homomorphism is a differential ideal, and the image of a differential subring, the image is the differential subring of the codomain, and the isomorphism theorems all hold. Woohoo! So we have first isomorphism theorem, among other things. But also the second and the third and the lattice isomorphism theorem, which I never quite explained to you guys. Sorry about that. I still need to draw you pictures of the lattice homomorphism. I never got around to that, did I? Okay. Lemma. Let R be a differential ring. And let C be the kernel of this differential homomorphism. Then that's a differential subring of R called the, if the derivatives, what is the C is for constants, right? The kernel of the derivative operator is called the constants of the ring. That makes sense? So if R is a differential field, then C is a differential field. Oh, that's neat. So up till now, we've only discussed that the derivative of the prime subfield of the differential ring or differential field differentiates to 0. This is extending that. You know, this set of constants could be more, like if we're looking at a subring which has the reals inside of it, then the constants should at least include the reals, maybe more, depending on what we're looking at. So Bill does have a proof here, and if you look at them, they're not that hard to follow. We probably can understand the proof of the lemma. Let's look at it. So 1 is in the constants because the derivative of 1 is 0. If we pick a and b in the constant, then the difference is the difference of the derivatives, which is 0. And by the product rule, the product is this, but again, a prime and b prime are 0, so that's 0. So we have the difference and the product is again in the constants. 1 is in the constants. What's missing? We have one last thing to do is to show that if a is in the constants, then a prime, well, that's the derivative, is equal to 0. That's also in the constants, right? So that's what it takes to show that C is a differential subring. And if R is a field, and we pick a in the constants with a non-zero, then as we discussed, you can build the derivative of the inverse like so. And so that shows the derivative of the inverse is 0, which says that a inverse is also in the constants. So there you go. That's the lemma. Let's see here. Any commutative ring with 1 is a differential ring when given... Oh, this is kind of stupid, right? You can take any commutative ring you want and define the derivative to be 0 on it. It's a differential ring. But you probably should say, who cares? I mean, great, but not... Yeah, I mean, yeah, who cares, right? Exactly. Apparently, Bill, since he put it in his notes, but fine. I can't complain. I paid nothing for these. I paid nothing for these notes. They're good notes. I mean, this is the result of my brother spending hundreds of hours to digest a couple of books in differential Galois theory down into about 15 pages. It's actually very nice what these are. Anyway, I should bring Bill to class, but I don't have money for that. What's that? Yeah, he lives in like Boone, North Carolina, so. And I think he's teaching right now, so there's that. But does he have off Friday? He probably does have Good Friday off, right? Because like. No. So he says it's interesting and strange to consider that Q adjoin pi, which of course is isomorphic to Q join X, is a differential field when given the derivation dd pi. So the definition of the derivative here would be that pi prime is 1, and like, you know, this is pi cubed prime is 3 pi squared, and so forth. And he says what this means is that R can be turned into a differential field in some very, very strange ways. Although I would add to this that, you know, this sophistication is known to my Calculus 1 students, because many times in Calculus 1 I have seen the derivative of pi cubed being 3 pi squared. It is not at all uncommon. Very, very popular. Very, very popular. You've seen it in 126, yeah?
I'm going to be writing 126. My analysis silliness like that.
Oh, yeah, yeah. Okay. Let F be a differential field of characteristic 0 and K over F be an algebraic extension, like we've talked about this semester. Then the derivation on F can be extended to a derivative on K in exactly one way. All right. So in other words, we can turn K into a differential field, and this can only be done in one way. So we can extend a derivative off the base field to an extension field, an algebraic extension, in a natural fashion. Here's how. Well, he just gives a sketch, but the complete proof is in this. I think that's a book. The full link, the full data on that is at the end of this PDF, all right? Anyway, here's the sketch. He says, let alpha be in the extension field and let f of x be the minimal polynomial for alpha over f, right? Then we can define the derivative of f of x formally in the usual way. And then he says, then f of x and df of x are relatively prime. Let's see here. Come on, where's his? I'm looking for his formula. How does he actually differentiate alpha? I mean, the essential thing here is that alpha has to satisfy, like, plugging into this being 0, right? So your derivative's got to respect that somehow or another, you know?
The last sentence.
In other words, d f alpha alpha prime plus g alpha is 0. What's g alpha? G alpha is this. Yeah, finally, he says define alpha prime to be g alpha divided by df alpha. Yeah, I think there may be a minus missing there, right? If we believe this. I think you're right. Why is df alpha non-zero? Alpha is the root of an irreducible polynomial. So alpha is not repeated. So when we differentiate f and evaluated alpha, it can't be 0. If it was, that would mean alpha is a repeated root. But that's not going to be the case because we're working with an irreducible polynomial. So admittedly, it would take me at least, 20 minutes of kind of sitting and tinkering before I understood this. But there is a well-defined path for extending the derivative to an extension field in this sense, okay? Let's look at some examples. The only derivation on Q is 0. Oh, because we've already proved that the derivative is 0 on the prime subfield, and Q is its own prime subfield. So if the derivative, once you have additivity in Leibniz that forces derivative 0 on the prime subfield, then if your field is the prime subfield, the only derivative is 0. So Bill's silly observation that the 0 derivative is a differential makes a differential ring makes a ring, a commutative ring with identity into a differential ring is not a vacuous comment. It's actually an important one for this example. So anyway, so the only derivative that you can define on Q is the 0 derivative. And so here's the minimal polynomial. What does he say? So shockingly, the derivative of the extension, the derivative on Q adjoin the square root of 5 is still the 0 derivative. All right, well, this is not especially, you start to wonder who cares, right? Let's get to the part that convinces you this is something actually interesting. Let f be a differential field. We call f of t over f a logarithmic extension if there exists some s such that t prime is equal to s over s prime, right? Does that make sense why you call that logarithmic? How do you differentiate log of s? How does it work?
The derivative of log x is
Oh, wait a minute. That's upside down.
Yeah. Because it's 1 over x times x prime.
Yeah. Well, it's kind of upside down, but. Well, I'm not sure that means this is wrong. It just means that I don't have a good intuition for it. Yeah. But so we'll accept his definition with a little bit of question mark. I feel like it should be s prime over s, but that could just be my naivete here. An exponential extension, if there is some s in f, such that t prime is equal to some s in s, such that t prime is equal to ts prime. That. So he says these mimic the defining properties of natural logarithm and exponential functions. If we integrate this, what's that give us? I think that's just a typo. I think it's supposed to be s prime over s. Yeah, I need to talk to Bill. You'll find me saying these same things 3 years ago when I talked about them in the class. I just always forget to talk to him. But I will try this year to have a talk.
Well, if you bring him to class, we can.
If I bring him to class, yes.
You should bring your wife to class.
So it's only like a 250-mile trip for him, but you know.
That's less than it takes you to get home.
It's less than it takes you to get home. That seems, that is an argument in the style of my wife.
Oh, you should bring her to class.
Yeah.
You've responded to what I've said with an irrelevant detail about your own life. That at first glance would seem to be an argument, but in fact is not. Yeah.
That's the way to do it.
That is.
Like, she should come, yeah, she should come and have.
So what you're like, what you're telling me then is that your wife is a woman. That is true.
Yeah.
But
So bring her
oh,
to
see, now I'm
class
going to have to edit that. Let's see here.
And then she could bring muffins.
Let's see here.
But also your kids.
So how about this one? Does this one make sense? If we integrate t prime over t equals s prime, that gives us like log t is equal to s. And then if you solve log t equal to s, you get t equals e to the s. I think this one might make sense in terms of solving. If we solve this differential equation, we get t equals e to the s. I agree with that. So anyway, so the above definitions yield formal characterizations of these functions without requiring us to actually work with actual fields of functions, right? And so here's the definition. A differential field with a field of constant c. A differential field extension is an elementary extension if there exists a tower of differential fields, like so, where each one of these extensions is either algebraic, logarithmic, or exponential. All right. So this is what's called a elementary extension. Either it's built from algebraic extensions, which we've already talked about in this class, you know, or these newfangled logarithmic or exponential extensions. All right. So, for example, he says if we take the field of rational functions, then E, and if E is defined to be the collection of all complex functions which lie in some elementary extension, C of x, then E is the field of elementary functions. So we can start with rational functions in a complex variable and look at all possible elementary extensions. That gives us the field of elementary functions. We're getting there. But I think, well, here's an example. Essentially, elementary functions are functions that can be built from the complex numbers, and you know, this function using algebra, exponentiation, and taking logarithms. So, for example, this is an elementary function, but don't try to take calculus 1. Don't try to tell calculus 1 that. It's not a wise move. So it's basically built from, you know, exponentials, logs, and algebra. Ooh. He said, keep in mind the elementary functions also include some functions which may be unfamiliar to us. For example, the bring radical is the unique real root of this. That's a elementary function. Ugh. Okay. Well, anyway, that's an unpleasant comment. I'm going to go past it. What about trigonometric functions? Well, trigonometric functions can be built from exponentials, imaginary exponentials. So that means that sine and cosine are elementary functions, as are all of their favorite reciprocal, relatives, tangent, secant, cosecant, cotangent, and their inverse functions. All of these are elementary. In other words, all of your favorite family of functions that we teach you how to write integrals as in Calculus 2, all elementary functions. Now this leads us to Leibniz's theorem, which characterizes which functions live in elementary extensions. I will not present the proof. I will just present the lemma and tell you the theorem. If we have a differential field with differential field extension f of t, and suppose that f of t and f have the same constants, and that t is transcendental over f, that means that it's not in an algebraic extension, right? And, well, then one t prime is in f, let's see here, and then f prime of t and the degree of f of t is equal to the degree of f prime of t if the leading coefficient of f of t is non-constant, and if the leading coefficient of f of t is constant, then the degree of f prime is 1 less than the degree of f of t. Nothing surprising here, really. And then this part 2 is a statement about how t prime over t works. Isn't that interesting? Now the derivative's upstairs. As you can see, basically this lemma says that things work like you'd expect them to for a logarithmic extension, okay? But that brings us to the theorem, Leibniz's theorem. If we have a differential field of characteristic 0 and alpha is in the field, if y prime equal to alpha has a solution y in an elementary extension of f with the same constants, then there exist constants, c1 through cn, and elements u1 through un and v and f such that alpha is equal to this. What is that saying? Saying you can build alpha from a linear combination of these things. These things are what? Things in the elementary extension, right? And yeah. I still don't think I've quite got to the punchline here. I'm hopefully Friday going to actually write things out more. This is kind of background material, actually, for the differential Galois theory. If you look at the proof here, it's basically partial fractions. It's all partial fractions. Partial fractions is actually really important to formal calculus. I think this is essentially the thing we're after. With Leibniz's theorem in hand, we can now show that various functions are not elementary functions. That means that we cannot integrate, all right, in the sense that we can't get an antiderivative formed by elementary functions. Of course, we prove in Calculus 1 that if the function is continuous, it has an antiderivative. But that doesn't mean you can actually find the formula for it in any nice way. To say it's elementary means you can find the formula in a nice way. Let f of x, g of x be non-zero. Suppose that g is non-constant. Then the integral of f of x times e to the g of x dx is elementary. If and only if f of x is a prime of x plus a of x times g prime of x for some a of x in there. So this gives us a concrete test for whether or not that integral is elementary. And he actually has examples. Again, I'll post this in course content for you guys as soon as I get a chance. So his first example, e to the x squared is not elementary. And here's the details for, why it's true. He says basically, okay, so if it was elementary, you'd have to be able to solve 1 is equal to a prime of x plus 2x a of x. And he goes through this argument to prove it's impossible. Therefore, e to the x squared is not an elementary function. You can't write the integral of e to the x squared in terms of elementary functions, as you're probably well aware. And he also shows that e to the x over x is not elementary, through some similar argument here. Is 1 over log x is not elementary. Arguments are there. So again, this little PDF was written by my brother, William J. Cook of Appalachian State University, and he's drawn from about half a dozen different sources. Crespo and I shouldn't even try to say that. This book, Algebraic Groups and Differential Go Theory. This looks like a, oh, Kluwer. Oh, that's expensive. Algorithms for Computer Algebra. Kaplansky, which is the classic, but a little bit old now, from 1957. This book here, this book here, this book here. And finally, Rosenlich has an article in the AMS Monthly. So, anyway, I hope that gives you some sense of, I mean, I don't expect that you could even check a given function was elementary or not, right? But I want you to make you aware that, like, this is theory, which is known. And so next time we'll talk about what's differential Galois theory. All right. So, thanks, guys.